Hello and welcome. For section 3.3, we'll be discussing the derivatives of the trigonometric functions, as well as derivatives and applications of derivatives for functions that include the trigonometric functions. We'll also be taking a look at some limits which involve the trigonometric functions, most specifically indeterminate forms of limits, which involve trigonometric functions and how to evaluate them by a variety of techniques. So to start with, I have included with this lecture the typed lecture notes. So you can see the 6 trigonometric functions and their derivatives. Okay, let's make a note right now. One note to make right now, that all of these functions, the input variable, in this case the input variable is x, or it could be t, or it could be theta. We take that input variable to be measured in radians, because that is the way we define the trigonometric functions over all real numbers. We do not in general choose the input variable to represent degrees, for example. We choose radians instead. Another note to make, you'll notice that some of these derivatives output what we could say would be positive expressions on the other side, not truly positive. Something like cosine could be negative, but it doesn't have a negative sign in front of it. But some of them do have negative signs in front when we take a derivative, right? The derivative of cosine outputs negative sine x. The derivative of cosecant outputs negative cosecant cotangent x. And the derivative of cotangent outputs negative cosecant squared of x. Okay? As a helpful reminder, the derivative of the 3 trigonometric functions that begin with the letter C, the derivative of the trigonometric functions that begin with the letter C will output a negative sign on the other side. That could be helpful to remember which ones output the negative and which ones do not. Some of the limits that we'll be looking at are based off of these 2 indeterminate form limits right here. Notice that if we try to just plug in theta is equal to 0 into this ratio, sine theta over theta, we would get the sine of 0 over 0, which is equal to 0 over 0 in indeterminate form. Well, that limit, it turns out, is equal to 1, and we'll show here a geometric proof in these notes for why this limit has to equal 1. And then we'll need to use it in actually deriving these formulas for the derivatives of trigonometric functions. The other limit also would be in indeterminate form. The cosine of 0 is equal to 1. So if you plug 0 into the numerator here, you get 1 minus 1, which is 0, divided by 0. So 0 over 0 in indeterminate form. It turns out that this limit here is equal to 0. Okay. I offer this limit here for you to prove after we have demonstrated how to prove the first one. I offer the proof of this one as a class exercise for you. I normally include it on your worksheet. Here's your worksheet as I would hand out in class, and at some point in the class session, I would ask you to practice this exercise right here. I'll let you know when you can do that. If you look ahead in the typed notes, you will see also worked out how to actually do the limit. But if you're interested in practicing it ahead of time, I'll let you know when you can try this one out on your own. Okay, if you want to pause the video and then try that out then. And then I would ask you to do this proof down here to prove that the derivative of cosine is in fact negative sine. And that is something I would ask you to do after we first prove together that the derivative of sine is equal to the cosine. So there's a couple exercises on the worksheet that are intended to be classroom exercises for you. And then several other, which are starting with finding the derivatives of the other 4 trigonometric functions. Okay, tangent, secant, cotangent, and cosecant. And then evaluating some limits of some indeterminate forms as well. And then, because we have an application problem here, this application here is in regards to harmonic motion, which is the kind of motion that would be undergone by a weight on a spring, for example. It is repeating behavior. Okay, in this case, a spring causing this object to move back and forth, or perhaps suspended, let's say suspended from the ceiling, and a weight that bounces up and down would be experiencing harmonic motion. It's simple harmonic motion if the amplitude and the frequency of the oscillation continues for all time, and it remains constant for all time, that is. If it, over time, if the object were to oscillate at lesser and lesser amplitude, maybe eventually until it actually even comes to stand still, that would be called damped harmonic motion instead. Okay. So we have an application here involving calculus, right? We're given a function that tells us the position of an object, a mass, and asked to find the velocity and the acceleration. That is, in other words, find the first derivative and the second derivative of this function with respect to time. The input variable t right here, okay, is measured in seconds. Okay, its unit measurement here is seconds. We interpret it as a real number, therefore we think of it as if it is a measure of radians and not of degrees. It's not an angular measure. It's thought of as the unitless input measure using radians. Okay, so the radian measure of a rotation can also be considered to be a unitless measure. We don't have to state that it's in radians. If it's the input to a trigonometric function and we don't state the units at all, we assume that it's just in radians. That is in general the assumption that we're going to make. So the radians are very flexible in being interpreted in a variety of ways. In this case, the input is being interpreted as a time value in seconds. Okay, the part B says what? Find the position, velocity, and acceleration at a given time. So you're going to have to be able to evaluate the trigonometric functions as well. Okay, and then some other functions which include trigonometric functions in them, and we have to find the derivatives. Okay, so we have some product rule, we have some quotient rule, we have some mixed up with polynomials and with the base e exponential as well. This one down here is the product of three functions, so it would require two applications of the product rule in order to differentiate this function just one time. Okay, you also have included here a set of trigonometric identities, the main identities that you should review from a trigonometry and a pre-calculus course. Some of these we use more than others. We're certainly going to want to know the reciprocal identities, that is, know how the six trigonometric functions are related to each other. Which ones are reciprocals of which other ones? Like the cosecant is the reciprocal of the sine function. The secant is the reciprocal of cosine. Cotangent is reciprocal of tangent. Okay, and then the tangent and the cotangent are ratios of two other trigonometric functions. Right, tangent is sine over cosine. Cotangent is cosine over sine. The Pythagorean identities, primarily this first one here, sine squared of x plus cosine squared of x is equal to 1 for any value of x. That's all real numbers. Large numbers, small numbers, positive, negative, 0. Okay. Sine squared of x plus cosine squared of x is equal to 1. As long as the angle is the same and you square these both and add them together, you get 1 every time. Manipulating this Pythagorean identity with the reciprocal and ratio identities from above, we can transform it into this identity. For example, if we take this identity, sine squared plus cosine squared equals 1, if we divide all three of these terms by cosine squared of x, notice what we get. Divide this by cosine squared, we get tangent squared. Divide this by cosine squared, we get 1. Divide this by cosine squared, we get secant squared, because 1 over cosine is equal to the secant. Right? Similarly, if we divided all these terms by sine squared of x, we would get 1 plus cotangent squared is equal to cosecant squared, the third Pythagorean identity. The even and odd identities, recall when we're looking at a graph of a function that an even function is one that is symmetric about the y-axis. And if we recall the graph of the cosine function, the cosine wave is symmetric about the y-axis. Hence, the cosine function is even. The sine function is an example of an odd function, and so is the tangent. An odd function's graph is symmetric about the origin. That is to say that if we were to take a function that has odd symmetry, if we were to rotate it through 180 degrees of rotation about a pivot at the origin, it would overlap itself. So any element that is any point or any feature in quadrant 1 would perfectly overlap with an identical feature in quadrant 3. And similarly from quadrant 2 to quadrant 4. For an odd function, that would be true. That's the type of symmetry we have. It's really, it can be seen as a rotation of 180 degrees when a function has an odd symmetry, but it's really also a double reflection. It is that if you flip the x values over and flip the y values over, which is what this is indicating here symbolically. And a function that has odd symmetry, if you change the input to its opposite and change the output to its opposite, you would find that you would just get a match with the original function. That is, in other words, if we move this negative to the other side, it would say the sine of x, the original curve y equals sine of x, is the same as negative sine of negative x. That's the sine of x curve is the same as itself being reflected both horizontally and vertically, two reflections. Meanwhile, an even function, which is, again, a reflection over the y-axis itself, we have only the input is being changed in sign. That is, for instance, any point that is in quadrant 1 is going to have a representative reflection in quadrant 2. That would be where the x value has gone from a positive in quadrant 1 to a negative in quadrant 2, but the y values of both points still remain the same. So we see there is no vertical change, no vertical reflection, for example, only a horizontal reflection. The fact that we have just x here, but the opposite of x here. Right? Tangent is an odd function. We change both the reflect both about x and y. This is about the y. This is about the y-axis here. This would be a reflection about the x-axis here. The cofunction identities can be seen by horizontal transformations of the graphs. For instance, the sine wave is exactly the same as the cosine wave. It describes the same behavior, the same periodic behavior. The difference between the sine and the cosine in terms of their graph and analytically as well is the starting point of the observation or starting point of the curve. The sine function starts at an equilibrium value, and the cosine function would start at either a maximum or a minimum. Okay. We'll take a look at, we're going to need a couple of these formulas here, the addition and subtraction formulas as well. If you want to dive deeper into that, where do you start proving these addition and subtraction formulas? Well, the initial proof is right here. You know, an interesting geometric proof that uses the distance formula in order to show that the cosine of a sum is equal to this expression right here. And then that immediately then leads to a whole bunch of other identities in this list. For instance, if s and t are equal to each other, then this is the same as the cosine of a double angle. That would be cosine squared of that angle minus the sine squared of that angle, right? If s and t are exactly the same as each other, you would have this double angle identity for cosine. Use of the Pythagorean identities from there gives us the other two. If you replace cosine squared with 1 minus sine squared, you would get 1 minus 2 sine squared. Similarly, for finding the last identity, replace sine squared with 1 minus cosine squared. Okay. Finding the sine of s plus t can be done by saying, well, look, the sine of any argument is relatable to the cosine of that same argument as long as there is an appropriate shift of pi over 2 radians. So since we already established that the cosine of s plus t is this, okay, then we could say, well, then the sine of s plus t is relatable to the cosine of s plus t. If the cosine of s plus t is already known, then we can find the sine of pi over 2 minus the quantity s plus t, and from that we can then establish what is the sine of s plus t. Anyway, so here's the formula right here. Okay, these are all relatable to each other. If you know the sine of s plus t and the cosine of s plus t, you could find the tangent of s plus t because the tangent is sine over cosine. Right? These are all inherently related to each other, by some of these principal formulas here. Okay, lowering powers formula. Okay, these can be established from the double angle formulas. You solve a double angle formula for the squared component, so sine squared. For instance, sine squared of x, you can subtract 1 from the cosine of 2x, divide by negative 2. All right, again, these are all related to each other. Take the square root of both sides here. You put a plus minus in front of the square root. You have the sine of x is equal to plus minus a big square root. Then if you replace 2x with u or some other variable of your choosing, like theta or something, well, if 2x is equal to u, then that means that x is equal to half of u. So this formula manipulated gives us a half angle formula over here. And the product of sum formulas are combinations that we can make out of these addition and subtraction formulas here. Okay, if you need any trigonometry review, I have plenty of content on that, or you can come discuss it with me in case you've forgotten anything important from your trigonometry course. And let me give you a quick introduction and definition of the trigonometric functions. We may know the trigonometric functions by their right triangle definitions, that is SOHCAHTOA. All right, so if we draw a right triangle without loss of generality, this could be, by any orientation, a right triangle. And if we choose some angle in here and call that theta, now I'm choosing theta to be an angular measure. That could be either in degrees or in radians. And again, I'll stress that radians are the preferred choice for a rotation, okay, and for the input when we're dealing with trigonometric functions because of the flexibility of the radian measure. And I'll get to the definition of the radian in just a moment. So right now, theta is an angular measure inside of a right triangle here. Relative to that theta, we have the side that is not the hypotenuse. Well, first, let's say the hypotenuse, right? This is the hypotenuse right here, always the longest of the three sides. Theta is always going to be opposite of. That is, if you are standing at the vertex containing theta and look outward into the triangle, you would be looking at the opposite side, and that is relative to where theta is. If instead we had been positioned ourselves at this angle up here, I'm using the letter alpha now to represent this angle, from relative to that position right there, the opposite side would have instead been this side down here, right? It's relative to which of these acute angles we happen to be positioned at, the one that we're calling the opposite side, okay, relative to that angle. And then the other side, the other leg of the triangle that is next to the vertex that we're standing at, but is not the hypotenuse side, that is called the adjacent side. Okay, and then we can recall the trigonometric functions by the acronym SOHCAHTOA. SOHCAHTOA. So, for example, the sine of theta is equal to the ratio of the opposite side length divided by the hypotenuse, right? And the cosine of theta is equal to the adjacent side length divided by the hypotenuse, CAH, right? And then the tangent of theta, okay, is equal to the opposite side length divided by the adjacent side length. Okay, we get the primary three trigonometric functions this way, and then we get their reciprocals by the reciprocal identities. The cosecant of theta, okay, that is the reciprocal of the sine of theta. So this would be the hypotenuse over the opposite ratio. The secant of theta, that's the reciprocal of cosine, so that would be hypotenuse over adjacent. And the cotangent of theta is the reciprocal of the tangent, that would be adjacent over opposite. Okay, so here are the right triangle definitions for the trigonometric functions. Okay? And then we visit those again in a trigonometry course to redefine them, okay, in what is, in many ways, perhaps the more common way of defining the trigonometric functions for application purposes, and that is within the unit circle. So I'll try to draw a circle here. The unit circle, okay, is a circle that has the center at the origin 0, 0, and the radius of the unit circle is equal to 1 unit of measure. All right. So maybe the radius is 1 foot, 1 inch, 1 centimeter, 1 mile, 1 light year, 1 astronomical unit, 1 unit, okay, of distance from the center to the edge. And the definition of a circle is that the distance from the center of the circle to any point on the circle will always equal that radius. It is a constant distance. Okay, so the radius is equal to 1 for the unit circle, and the center is the point 0, 0. Now, the equation of the unit circle then is x squared plus y squared is equal to 1, based on the distance formula and the definition of a circle. Okay, so any combination xy that satisfies this equation is going to be a point that is on the unit circle. Now, we define the trigonometric functions this way. We imagine this is the initial point right here. That would be the point with coordinates 1, 0. That is the x-axis. The positive x-axis goes in this direction, or t-axis, we'll call it the x-axis. Okay, and then the positive y-axis moves in this direction. Right? Okay, if we are to travel along the unit circle, we can do this either in the counterclockwise direction or clockwise direction, but we say that if we are choosing a positive rotation is considered to be in the counterclockwise direction. So this would be a positive rotation right here. If we were to travel along the arc of the circle itself, that is, we have traveled through an arc length, right? A curved length. The length, the distance we have traveled, we're going to call that t when we're dealing with the unit circle. When it's not the unit circle, if r is not equal to 1, we would call the arc length s. It is a distance measurement. But we use t as the value for arc length when we are in the unit circle. Okay, so t is the arc length in the unit circle that we traveled, and we are traveling from the initial point 1, 0. If we start at 1, 0 and we travel a distance t, okay, we will end up at some point that is on the unit circle. And whatever point that is, it has some coordinates x, y. And those coordinates x, y, because this point is on the unit circle, those coordinates must satisfy this equation. Right? The sums of their squares must equal 1 because this is a point on the unit circle. Okay? And now this is how we defined the trigonometric functions. In the unit circle, set up this way, the x coordinate is the cosine of that distance t. And the y coordinate of this point is the sine of that distance we traveled t. T is a distance. It is an arc length. Right? It is a distance. It is an arc length. Now, we can relate that distance to a central angle of rotation as well. That is, we can say, well, we know, for instance, that the larger the distance we travel, we can see this, right? You can observe this geometrically. The larger the distance that we travel along the arc, the larger of a rotation we would have had at the center of the circle to get there, right? So there is a relationship between this distance we traveled here and this rotation we had in here. And let's call that theta. Right? So theta is the variable to represent the rotation at the center, but t is a variable to represent the distance we traveled along the unit circle. That's when the radius is equal to 1 specifically. Okay? And now, since t and theta are so closely related to each other, right? If t is negative, for instance, we would have moved in this direction. Well, then theta would have been negative as well, because we would have rotated in that direction, right? So since they're so closely linked to each other, what we say is simply this. We're going to define now the radian measure of a rotation, okay? The radian measure of rotation this way. Theta equals t if theta is in radians. That's it. Really, we allow this to work if we're not in the unit circle necessarily at all. We actually say that theta is equal to s over r, okay, where s is in fact the arc length, okay, the value for arc length we would use when r is not equal to 1, for instance. So more generally, this is actually how we define radians, okay? This is how we define radians, not degrees. So now, for instance, like if we went through 45 degrees of rotation, that does not correspond to a distance of 45 units of distance. Right? No, not in degrees. But if we said we traveled through 1 radian, right, 1 radian of rotation in a unit circle, that's where r is equal to 1 unit of distance, that 1 radian of rotation would correspond to 1 unit of distance along the rim of the circle. So let's say that the unit circle were defined where the radius was 1 meter. Let's say the radius is 1 meter. Then if we rotate through 1 meter, if we rotate through 1 radian of rotation, that would correspond to 1 meter of distance we would have traveled along the arc of the circle. So now if we went through, let's say, pi radians of rotation would correspond to pi units of distance along the rim. And because the unit circle has a radius of 1 and the circumference of a circle is 2 pi r, then the circumference of the unit circle is just 2 pi. Right? So if we know that we went this distance halfway around the circle, if we just went halfway around the circle, that means we have traveled a distance of pi units, pi meters of distance. And because of the way we define the radian measure, we then say, therefore, we have rotated through exactly pi radians of rotation to get halfway through the circle. All right, so since c is equal to 2 pi times 1 is equal to 2 pi in the unit circle, okay, then one rotation through the unit circle must correspond, right? Now, circumference is a distance, right? We're saying that if the distance around the circle is 2 pi, then one rotation through the unit circle corresponds to where theta would equal 2 pi radians. And that way the amount of rotation we have, right, the amount of rotation is exactly equal to the amount of distance we traveled when we're in the unit circle. So it is the radian unit of measure that allows us to take the quantity of the rotation here, in this case 2 pi, and ignore the units entirely so that we can interpret this 2 pi at will as either a rotation or a distance, because the two are going to have the same value. Right? Now, degrees don't offer us the same flexibility, and the radians are designed to give us exactly that flexibility. Now, notice, if we just say that because of the way we define the trigonometric functions here, if x equals cosine and y equals sine, well, plug cosine in for x and sine in for y, and what do we get? You get cosine squared t plus sine squared t equals 1, which is exactly the Pythagorean identity, right? The first of the 3 Pythagorean identities. Okay, now the connection between these two is through the Pythagorean theorem. That is through the right triangle trigonometry and the unit circle definitions of the for trigonometric functions. The connection is through the Pythagorean theorem. And the Pythagorean theorem here, in the right triangle here, we could say is, the adjacent side squared plus the opposite side squared is equal to the hypotenuse squared, for example, right? And in the unit circle we have, well, the actual equation of the unit circle itself is derived right from the Pythagorean theorem as well. If we were to take for any point such as this right here, if we were to drop a line perpendicular to the x-axis and make a little right triangle, then just based on the fact that the coordinates here are x, y, this length of the triangle is x, this length of the triangle is y, this length is 1. And by the Pythagorean theorem, we get x squared plus y squared is equal to 1 squared, or x squared plus y squared is equal to 1. And that would be true throughout the entire unit circle, as long as we were at a point where we could construct a complete right triangle. That is, as long as we're not ending on one of the axes, the x-axis or the y-axis itself. Right? This equation will still be true, though, even if we ended on the x-axis or y-axis itself. I'm just saying that we wouldn't have a right triangle. Right? If we had a point like right here, we're not able to construct a right triangle there. Okay, but we're still going to have the relationship x squared plus y squared is equal to 1, even if we end up on one of these axes. Okay, so now let's start taking a look at derivatives of trigonometric functions. Let's start by defining the derivative of the sine of x. Let's find out what is the derivative of the sine of x. So here I'm going to write out the limit definition. The limit as h goes to 0 of the sine of x plus h, assuming that x is in radians now, okay, sine of x plus h minus the sine of x over h. And of course, if we try to plug 0 into this for h, we're going to get 0 over 0 in indeterminate form, right? Now, how do we evaluate this indeterminate form? We can't factor this. This is not polynomial. We're not going to be using a conjugate here as well because we're not looking at square roots even. So what can we do? Well, we have a sign of a sum right here, right? Let's try expanding the sign of a sum. And well, here's the sign of a sum right here. The sign of the sum s plus t would give us the sine of s cosine t plus cosine s sine t. Okay. So let's use that. Limit as h goes to 0, okay, the sine of x times the cosine of h plus, now we're going to take the sine of h times the cosine of x. Okay, and then we are subtracting the sine of x as the last term, and then this is all over h. Okay, all right, so we have 3 terms here in the numerator. Okay, so we have the limit as h goes to 0 of, we have the sine of x, all right, times the cosine of h over h, okay, and then we have plus the sine of h cosine x over h, and then minus the sine of x over h. Okay, I'll take a look at where the h's are in these expressions. Let's see, we've got an h here, over here, an h here, over here, and then here we just have an h in the denominator. Okay, and x is, well, x is taken to be constant right now because it's h that is currently in motion. Okay, well, here's what's going to work. We can combine the first term here and the last term, okay, together to get this, the sine of x times the cosine of h minus the sine x over h, like that. And then this term, okay, I'm going to do this. I'm going to take the sine of h over h, that's that limit that we're going to be looking at in a moment, and then that's times the cosine of x. Okay, and then the other limit we're going to be looking at in a minute can be found by factoring out sine of x from this numerator here. So we can take out the sine of x, and that leaves us with the cosine of h minus 1 over h. Okay. There we go. So in order to find out what this is equal to, we're going to have to evaluate this. We have the sine of x, which is constant right now with respect to h. This is constant. So we have the sine of x times the limit as h goes to 0 of the cosine of h minus 1 over h. If you try to plug 0 into this limit, okay, you're going to get 0 over 0. The cosine of 0 is 1. So 1 minus 1 over 0, which is 0 over 0. Okay, I'm going to put that h in parentheses, only because I don't want to, well, later we're going to see another function, the hyperbolic cosine, which is called the cosh, abbreviated COSH, but this is the cosine of h. Okay, so that's this term right here, and then the second term, we can factor out cosine x, okay, because it is constant with respect to h, and then we have the limit as h goes to 0 of the sine of h over h, and again, this one's going to output 0 over 0, indeterminate as well. These are both indeterminate. So we need to figure out what those two limits are equal to. Now, how do we establish what these limits are equal to? I'm going to, using our definitions of the trigonometric functions, let's go use some geometry as well, okay, and take a look at the proof I've included here in the notes. So here's our definition of the trigonometric functions. We have x equals cosine of t, but since t and theta are the same as each other, then x equals cosine of theta, right? Remember, t is the distance, the arc length distance in the unit circle, and theta, as long as it's in radians, is exactly equal to what t is. And similarly, the sine of t is equal to the sine of theta. Okay, and here's our drawing representing that. Now let's extend this geometry outward a little bit in order to do our proof that this limit here, sine theta over theta, is equal to 1 when theta goes to 0. Okay, we're going to use geometric proof. So, as the trigonometric functions are defined, this height of this right triangle right here the y coordinate is equal to the sine of theta, by definition. And this leg of this triangle here, the x coordinate, is by definition the cosine of theta. So we have sine of theta here, cosine theta here. Now I'm extending this line out here from the center through B until it reaches a point up here that would be where it would intersect the vertical line that goes through this point A. Okay, so there's a vertical line through here that I'm calling, that's this line segment AD right here. Okay, and we're extending the line segment OB out until it intersects at D, and so that's where this comes from. So this is zoomed in on this quadrant right here. Okay, so the length of this green arc, the length of that is t. The amount of rotation here is theta, and t and theta are equal to each other. Now notice we also have similar triangles. That is, this triangle OCB, that right triangle there, is similar to OAD. That is, they have the exact same angle measures. They both share this angle here. They both have a right angle in them. And because the angles in triangles on a plane add up to 180 degrees, well then this angle here and this angle here must be equivalent as well. So these are similar triangles. And from geometry we know that the ratios, this is important in understanding the trigonometric functions anyway. No matter how large or how small the triangle is, if the angle that we're interested in isn't changing, the ratios of sides will always be the same, right? So the ratios of sides in similar triangles are always equal. So for example, relative to this angle here, the ratio of this side to this side in the smaller triangle, sine of theta over cosine theta, okay, the sine of theta over cosine theta must be exactly equal to the ratio of this side AD, whatever that is, divided by this side OA. But we know the length of OA, it came from here, the distance from the center of the circle to A, and that length must have been 1 because it's the unit circle. So the ratio of sine over cosine is equal to the length of AD divided by 1. In other words, the length of AD is sine over cosine, which we also know as the tangent. So the length of this red line segment is the tangent of theta. Okay, the tangent of theta is the length of this red segment here. So I explained that a bit down here as well. Okay, if you want to see that. Okay, now we can compare this length right here, which is sine theta, to this length, which is tangent theta. And clearly from this picture, the sine of theta is less than the tangent of theta. They could be equal to each other if the angle was 0. If the angle was 0, this wouldn't be a triangle at all, and then these would just be 0 right here. Okay, but in the case where we're actually in quadrant 1, in fact this would be true in any other quadrant as well, we can see from the picture quite clearly that this length is less than that length. So the sine of theta is less than the tangent of theta. But also, the length of this arc, the length which is t, is the distance. That distance is greater than the sine of theta. We can see that it is, that the fact that it is curved, it is greater than sine of theta, but also that t is less, okay? The distance along this curve is less than this distance here. So we'll recall that, again, t is exactly the same value as theta. So we can say this is theta. Okay, so the sine of theta is less than or equal to theta, and theta is less than or equal to the tangent of theta. Okay, to justify that theta is less than or equal to the tangent of theta, one way we could do that is graphically. We can graph the line y equals theta versus y equals tangent of theta on the same screen. So to justify that for you, just wanted to show you that I was going to do that. So I'm graphing y equals the tangent of x. That would represent that graph, then the y values of that graph would represent the length of this side for various values of x, and y equals x, which would represent the length of this. Okay, so if we graph those two, okay, on the same screen here in quadrant 1, you can see the curve y equals tangent of x, okay, is, except at the intersection point here at the origin, that curve, we can zoom in to see even more so, that curve tangent of x is always above the graph of y equals x. So that is, anytime we're in quadrant 1, this length right here of this side is always going to be more than this curve right here. Okay, so this construction establishes that the sine of theta is less than or equal to theta, which is less than or equal to the tangent of theta. And let's pick it up there symbolically down here. Here's the conclusion. This is two inequalities that we can then look at. The sine of theta is less than or equal to theta, and theta is less than or equal to the tangent of theta. Now, if we divide the first inequality, as it says here, by theta, which we are in quadrant 1, so theta is positive, dividing both sides of the inequality by a positive quantity preserves the direction of the inequality. So that gives us the sine of theta over theta is less than or equal to 1. If we, on the other inequality, rewrite tangent of theta as, by identity, sine of theta over cosine theta, right, we get this. And that's the same as now if we multiply both sides by cosine theta and divide both sides by theta. Again, because we're in quadrant 1, everything is positive in quadrant 1. We could make this work in other quadrants as well. We would just have to be applying some absolute values, for instance, in order to make this work right. So we multiply by cosine theta, which is positive, and divide by theta, which is positive, so we preserve the inequality direction. Then we get the cosine of theta is less than or equal to sine theta over theta. Now we can combine these two inequalities so that the sine of theta over theta is bounded between cosine theta as the lower bound and 1 as an upper bound. That's this right here. Now, in order to evaluate this limit in the center, we can apply the squeeze theorem because we have a lower bound and an upper bound. We have a limit that we're trying to evaluate, so we can take the limit on the left and the limit on the right as theta approaches 0. Now, the limit on the right is just constant. It's 1. So the limit on the right is just going to be 1. And on the left, as theta goes to 0, well, the cosine function is a continuous function, so we can just evaluate that limit on the left by just plugging 0 into the cosine. And the cosine of 0 is equal to 1. So, therefore, the limit as theta goes to 0 of sine theta over theta must also equal 1. Okay? So we have proved that first limit, sine theta, the limit of sine theta over theta is equal to 1. Now we're going to use that back in our definition of the derivative as we're deriving the derivative of the sine function, right? Where can we use that? We now have this limit right here. We've just established that this limit is equal to 1. And so we're left with the cosine of x times 1. Now we still have the sine of x over here, and then we're multiplying it by whatever this limit equals. And once we figure out what that limit is, we'll then be able to establish ultimately what the derivative of the sine of x is. So now to figure out what this limit is. And that would be where we go in class, say now would be a good time for you to pause the video and see if you can figure out what this limit is. And it's not going to be nearly as tough as the geometry that was just done on the previous limit. Instead, you do this, you don't need to use geometry on this particular one. There's a hint for you. You can use a technique that we've already discussed in this class before that is going to allow you to use identities in order to relate this to the limit that we just did a moment ago. So now would be a good time to try that out if you want to give it a try on your own. Prove this limit algebraically. And if instead you would like to see how the limit is derived, and we can go back to the notes over here, establish the technique that I was talking about, that we had talked about earlier in the semester, is a technique of, in fact, using the conjugate. Now, not because we're looking at a difference of square roots necessarily right here, it doesn't look like we are, but because of the fact that we have the Pythagorean identity that we would be able to apply. Right? If we have differences of squares with trigonometric functions, the differences of squares, okay, are useful to us because of the Pythagorean identities. So if we multiply in this case by cosine theta plus 1 over cosine theta plus 1, as you see here, you get cosine squared theta minus 1. But the cosine squared theta minus 1, that's exactly negative sine squared of theta. Right? By the Pythagorean identity right here. Cosine squared of x is equal to 1 minus sine squared of x. Okay. So you can replace cosine squared of theta by 1 minus sine squared of theta. And then combine like terms, the 1 minus 1 cancel each other out, and you're just left with a negative sine squared theta, and that's it in the numerator. Right? Now, if you try to run the limit at this point, plug in theta is equal to 0, you're going to get the numerator is 0, and the denominator is 0 because of this theta right here. So, we have to figure out a way to cleverly manipulate this expression to remove the discontinuity, the 0 over 0 removable discontinuity. So what we do, we can factor out the sine theta over theta, right? And now we know we can run this limit, because we just established that this limit here is equal to 1, right? The limit as theta goes to 0 of sine theta over theta, that's just equal to 1. And we can run this limit and multiply it by this limit as long as both of these limits exist, right? So this one is equal to 1. What's this one equal to if theta goes to 0? Well, the numerator will go to 0, but now the denominator here actually goes to 2, because the cosine of 0 is equal to 1, so we have 0 over 2. So we end up with 1 from this limit times 0 from this limit, and 1 times 0 is equal to 0. So this limit, okay, whether we're using theta or h or t, right, or x or delta x as our input, okay, this kind of a limit here is equal to 0. So back to our derivative of the sine. So this limit right here, therefore, is equal to 0. That means we have sine of x times 0 plus cosine of x times 1. And that leaves us with the cosine of x. That is, we've just established, by the definition of the derivative, okay, that the derivative of the sine of x with respect to x is equal to the cosine of x. Okay, now it's quite similar what we can do to find the derivative of the cosine of x to show that the cosine of x, the derivative of cosine of x, is in fact negative the sine of x. And that is the next exercise for you to work on with your worksheet now. Okay, we already have these two limits established, and you're going to need to use those again in the proof. Okay, but we've already have everything else in place that you need. Using the limit definition of the derivative for cosine of x, okay, show that the derivative of cosine of x, take the limit as h goes to 0 of cosine of x plus h minus cosine x over h, okay, use an identity to expand the cosine of x plus h, okay, collect the terms appropriately, and then try to see where you can apply these limits to prove that the derivative of cosine of x formulaically is negative sine x. So you can try that on your own right now as an exercise. And if instead you'd like to see how the proof is worked out, okay, I include that in the notes as well. Here we are. Nope, that was next one. There it is. All right, so you expand the cosine of x plus h by the use of the cosine of a sum identity, right? So you get cosine cosine minus sine sine. Okay, collect the terms. You find these limits here that pop out, so you get the limit of this one is 1, the limit of this one is 0, so you end up with negative sine x. Okay, now the other way to demonstrate that these results are at least reasonable, and this certainly proves that they have to be, the derivative of sine is cosine, but the derivative of cosine is negative sine. Okay, remember, the ones that start with a c, the trig functions that start with a c, their derivatives will have a negative, okay, in front of it. Okay, the other way to see that this is reasonable is to consider the graphs. Just like we did with section 2.8, where we had a function, and then we can construct the graph of the derivative of that function. So, for instance, let's prove, or let's demonstrate that the graph of the sine of x, okay, has a derivative to its graph that seems to resemble the cosine, and we see that here. This is the sine wave. Right, it goes through equilibrium at 0, 0. That's if an object were bouncing up and down. If you had a weight hanging from a spring, let's say, you know, from the ceiling there was a weight hanging from a spring and it was just relaxed there and it was just hanging out. This is where it would just be hanging out at this height. Let's say the ceiling is up here and it's pinned to the ceiling and it's just hanging here. And so you come into the room and you grab that weight and you pull it down a distance, a displacement, and then you release it and it starts bouncing up and down. Right? It's now it's now undergoing harmonic motion. It's simple harmonic motion if it doesn't, if the amplitude doesn't decay over time. But if it ends up going, over time back to equilibrium again, then that would be damped harmonic motion. Okay, but that idea of where is at rest, where does it want to rest when it comes back to being still again? That height would be equilibrium. Okay, so here's the graph of the sine x, and what is its derivative going to look like? Remember from 2.8, we said we could start by looking for points that would have horizontal tangents. Anytime we have a point that would have a horizontal tangent to it, notice of course the slope is 0, then the derivative, f prime, would have an x-intercept, that is a 0 of that function. And so each one of these horizontal tangents corresponds to a point on the derivative curve where it crosses the x-axis. Okay. We also talked about wherever we had points, they're called inflection points, most of the time inflection points, whereby, so you can see an inflection point if it curves over, like this is like an inverted bowl, a bowl that's upside down, but at this point it turns into a bowl that is face up instead. That point where the curvature changes from over to under, or also that changes from under to over, that would also be an inflection point right there. Those points also indicate on a nice smooth curve where you have the maximum rate of decrease, that is the steepest downhill slope that we can get, or the maximum rate of increase. So maximums in the rates of change by maximum values of the slope. This would be a maximum and absolute value. So this is the maximum possible positive slope. This would be, I should call this a minimum. This would be the minimum slope. So it is the largest possible negative slope that we would see within this interval. So this shows up as a maximum point on this curve, on the derivative curve, but this at pi would show up as a minimum point on the derivative curve. So put those pieces together where the zeros are and the maxima and the minima, okay, and we end up with a nice smooth curve that looks like this. And this is exactly the graph of the cosine function. It starts at a maximum, and that maximum happens to be 1. It crosses first at pi over 2, and that's exactly where the cosine is equal to 0, right? Cosine of pi over 2. Also equal to 0 at 3 pi over 2, which also then corresponds to a minimum and a horizontal tangent line on the sine function. So it seems reasonable that if we sketch the derivative of the sine curve, we get a curve that looks like the cosine function. And similarly, if we take the cosine curve, here's the cosine curve then, if we look at its derivative, what do we get? Okay, so we have horizontal tangent line here, so that corresponds to x-intercept. Horizontal tangent line, x-intercept. Horizontal tangent line, x-intercept, right? And then we take a look at like where the inflection points are, for instance. And along this interval here from 0 to pi, all of the slopes of tangent lines are negative. And it's going to be the most negative at pi over 2. So we're going to get a minimum at pi over 2, and all negative slopes throughout there. So we go from where we were at 0 as the slope, okay, to the next point where we're at 0, which is at pi, and between those two, the derivative is entirely negative. So this. And so on and so forth as we extend this outward in both directions. So this is a curve, a wave, a trigonometric wave, that crosses through equilibrium. Well, a sine function crosses through equilibrium at the origin. But this is the reflection of the sine curve, right? Because the normal sine function would start by going up, would be increasing from 0 to pi over 2. But this is decreasing from 0 to pi over 2. So it seems reasonable that the derivative of the cosine, by looking at the graph, would be the negative sine function, negative sine of x. Okay, so we get that vertical reflection that causes the wave to go down first into as x is greater than 0. Okay, so we've established those first two trigonometric derivatives now, and we took a look at a couple of these limits here. Okay, now let's say we wanted to find some more of these derivatives here. All right. Let's try it out. Let's take the derivative of the tangent. Let's prove that the derivative of the tangent of x is in fact equal to secant squared of x. Okay, and then I actually want to go even further than that. I want to find the second derivative. All right, we know we can do that. Anytime we can differentiate a function, we can see if we can differentiate it twice. Okay, then we have applications. If we're dealing with these harmonic motion applications, the position functions, we can talk about what is the velocity of the object bouncing on the spring, or what is the acceleration, for example. And also the jerk or the snap that we talked about, which is the third derivative, right? Which would be useful, if you're designing features, mechanical features that have springs in them. Like, for instance, think about if you're designing a car with shocks, where you want to minimize the jerk. That is the third derivative of position. You want to minimize the jerk so that the passengers have a smoother ride. Or if you're designing an amusement park ride, like a thrill ride, like a roller coaster, or some sort of a free fall or something like that. And in order to give a more thrilling experience to the rider, you may want to focus on trying to maybe increasing the snap or the jerk, the third derivative, so that they experience more of a jolt in the acceleration as it changes, as it go around curves and go and go over hills and things like that, right? So applications we have for the derivatives of position functions. Okay, let's just find y prime and y double prime for the tangent function. Y equals the tangent of x. Okay, and we won't have to go through all those hoops we just went through with sine and cosine to do it. Instead, we're going to use a combination of our trigonometric know-how, okay, and the calculus that we've been studying recently, starting with some trigonometry. Tangent of x, by identity, is equal to the sine of x over cosine of x. In fact, all the other four trigonometric functions, they are all based on the sine and the cosine, right? You can write any of the other four trigonometric functions in terms of either sines or cosines or both. So now that we already know derivatives of sines and cosines, and because we already know how to take derivatives of quotients by the quotient rule, then we now have everything we need to find the derivatives of all the trigonometric functions. Okay? So let's find y prime right now by use of the quotient rule, because we have a quotient sine x over cosine x. And the quotient rule is, we remember it as low d high minus high d low. Don't forget the square below, right? Or low low. Okay, so we start with low, which is cosine x, times d high. So I'll write it out here. We're taking the derivative of the sine of x, minus high, so that's sine of x, times derivative low, so derivative of cosine x. Okay, and all of that over the denominator squared, so cosine squared of x. Just recall that, for notation, cosine squared of x, okay, is different from cosine of x squared, right? These are not the same as each other. Here, we're squaring the cosine function. That is, we are saying this is interpreted as cosine x times cosine x. But this is interpreted as cosine of x times x. All right, and those are not the same as each other. Okay. And another note that that is worth mentioning as well, because you can see it a lot in work with trigonometry, and it is an issue. You need to write the argument. So if you write something like derivative of sin is equal to cos, that is incorrect notationally. Okay. All right. Makes sad math graders. Okay, that's sad, not angry. That just makes me wonder, why did you do that? Okay, so the derivative of sin is meaningless. That's like saying, what's the derivative of square root? It's really as ludicrous as that. The square root symbol all by itself is not worth any value. It is not doing anything. Until you actually put a quantity in it, it doesn't mean anything other than it's just waiting for you to give it something to do. And that's what it looks like when you write something like this. If you ever see something like this on paper, if you're literate in mathematics and you have to read this work all the time, okay, this is difficult to look at. So please don't write that. Okay, what you mean to write is the derivative with respect to x of sine of x equals cosine x. Okay, or perhaps derivative with respect to t, sine of t equals cosine of t. Now that would be correct. Okay, notationally correct. Okay. Oh. Okay, so please include the argument inside of your trigonometric functions. Okay, notationally. All right, continuing here. Y prime is equal to what? Well, we got cosine of x times the derivative of sine, which the derivative of sine is cosine x. And then we have minus sine x, and then we need derivative of cosine with respect to x. The derivative of cosine is negative sine x. And the denominator is cosine squared x. So we get cosine squared x plus sine squared x over cosine squared x. Where do we go from here? Right? Trigonometric identity. Simplify this. We have the Pythagorean identity. The Pythagorean identity, cosine squared x plus sine squared x is equal to 1. So this equals 1 over cosine squared x. Let's go even further. Okay, now we're going to use reciprocal identity. 1 over cosine x is equal to the secant of x. So y prime is equal to secant squared of x. Alright, so that is the derivative of tangent is secant squared. Okay, so the derivative with respect to x of tangent of x is equal to secant squared of x. Okay, we did not use only calculus here, right? We used some trigonometry as well, right? We used an identity right here, okay? Then we used the quotient rule right here for calculus. So we went from trigonometry to calculus. Okay, we completed our calculus step right here in the quotient rule as well. Then we used a Pythagorean identity and a reciprocal identity. So 3 trigonometric identities, 1 technique from calculus, okay, in order to get a nice simplified result here to prove that the derivative of tangent is secant squared. Now, find the second derivative. That is to take now the derivative of secant squared of x with respect to x. How can we do that? Well, we don't yet have the derivative of the secant, and we can find that soon enough, but we do know the derivative again of cosines. We can always write any of our trigonometric functions in terms of sines and cosines. Okay, so we can write that the secant of x is equal to 1 over cosine x, for example. So we have y equals, or this is y double prime, that y double prime, the second derivative, is the derivative of 1 over cosine squared x. Okay. All right, and now to do this, okay, we're going to need to write this as a product. We got 1 over cosine x cosine x. Okay, so the denominator here is now a product. So y double prime, okay, we have a quotient here. Let's use the quotient rule. Okay, low d high, high d low, over low low. Okay, so we start with cosine squared x, okay, that's the low function, derivative of the higher function, right? Derivative with respect to x of 1, and the derivative of a constant will be 0, minus the high function, which is 1, times the derivative of the bottom function. We need the derivative with respect to x of the product, cosine x times cosine x, okay, over the denominator squared. So what is that? Well, the derivative of 1 is 0, so we have cosine squared of x times 0 minus 1. Now we need the derivative of cosine x cosine x. So this is going to require the product rule. All right, so we can take, let's see, the derivative of the first, okay, the derivative of the cosine is negative sine, and multiply that by the second function, which is cosine. And then add to that, we can leave the first function alone, which is cosine x, and multiply them by the derivative of the second function. Okay, so that right there, this right here, is our use of the product rule. Okay, so we had already used the quotient rule one time right here, and within the quotient rule we needed to apply a product rule at this stage. Okay, and then this is all over what? Cosine to the fourth of x. Now the first term is just 0, right? It's canceled out, that's 0. And then let's see, we have a negative sine x cosine x, another negative sine x cosine x, so those will combine to be negative 2 sine x cosine x, but then there's a negative here, that'll flip it to positive. So we get 2 sine x cosine x, which by the way is the same as the sine of 2x, it happens to be, the double angle. Okay, and then we have the cosine to the fourth of x down here. Okay, we can cancel a cosine with a cosine. We have 2 times, let's see, I can write this as sine x over cosine x. Okay, we cancel a cosine with one of these cosines, and then there's 2 more cosines in the denominator, so I'll call that 1 over cosine squared x. And now we use some identities, and we'll say then y double prime is 2 times the tangent of x, sine x cosine x is tangent x, times secant squared x. So I got the second derivative here of the tangent function then, okay, by taking the first derivative of secant squared. Okay. Now, in order to deal with the square, at this point we had to write it as a product, but we didn't have the derivative of secant x. We can find the derivative of secant x, but we didn't have it yet. So instead I wrote secant in terms of cosine. Okay, we had to use a quotient rule and we had to use a product rule. We also had to use some basic identities here in order to get this particular simplification that I have right here. Now, you can see what the derivatives are for the other 3 trigonometric functions here, like the derivative of secant x is secant x tangent x. Okay, one of the exercises on the worksheet is for you to prove that that is true. Okay, find the derivative of the secant x. Okay, secant of x by taking the derivative with respect to x, and prove that it equals this, secant x tangent x. And you can do so by, again, use identity, and then use quotient rule, okay, and then simplify by the use of other identities, again, in trigonometry to show that you get this result. And similarly for the cosecant and the cotangent to show that you can get these derivatives as stated here. Okay, let's take a look at some other limits. Okay, using these 2 limits right here and some other algebraic technique like substitution and maybe some ingenuity, maybe the use of a conjugate, things like that, we can evaluate some other indeterminate forms of limits involving trigonometric functions. Okay, so I have a few here. You know, you can take a look through on the type notes. We can talk about a little bit here. Here, this limit. Limit as x goes to 0 of the sine of 3x over x. At first glance, we might say, well, look, you plug in 0, you get 0 over 0. And maybe that's just equal to 1, because the sine of x over x, that went to 1. Okay, so let's see if we can justify why the answer to this is not 1, but in fact the answer to this happens to be 3. Okay, the way we justify it is, we can say, well, let's do a substitution. That is, we can rewrite this instead in the form sine theta over theta, where theta goes to 0, which we know would equal 1. And that means the 3 itself gets absorbed somewhere else. So we do it this way. Change the argument to be theta. We can replace 3x by theta by choosing theta to equal 3x. So that allows us to rewrite the numerator as the sine of theta. Then the denominator, which is x, we can just invert our substitution. If theta equals 3x, well then x is theta over 3. So we can rewrite the entire ratio then, the sine of theta over 3. But we're no longer now taking the limit as x goes to 0, because we don't have x anymore. We've changed the variable from x to theta. Now we don't just automatically say then theta goes to 0. It has to do with the substitution we selected. We chose that theta and 3x were equal to each other. Now since x was going to 0 in the limit, we apply that to this equation. As x goes to 0 on the right-hand side of this equation, notice that that means the right-hand side goes to 0. which means theta is going to 0 as well. In order for these two sides to equal each other, right, when x goes to 0, it must be that theta goes to 0, because they're equal to each other, right, the way we set it up. So when we change the variable from x to theta by this substitution, we end up changing the variable in the limit as well. And in this case, for this substitution, theta is going to 0, the same as x was going to 0 before, because of the substitution. Okay, so I just wanted to stress that's where that information is coming from. It's not automatic, but it has, you know, how x got replaced by a function of theta and how the variable in the limit got changed. Both of those were consequences of the substitution we selected. And we chose a substitution so that we would end up with the sign of theta, because then we can relate it back to the original limit that we were already looking at, a limit where it was the sign of theta, not the sign of 3 theta, but the sign of theta. Okay. Now, if theta was already being used, we might choose a different variable like u, for instance. We could choose u to equal 3 theta or 3x or something like that. Okay, I'm just choosing one to make it look more familiar, like what we already did. Okay, so simplifying this, you have to factor out this 1/3 from the denominator. Well, dividing by 1/3 is the same as multiplying by 3, and it's a constant, so we throw that in front of the limit. And now this limit right here is the limit that we already know. That limit is 1, so we have 3 times 1, which gives us 3. So showing algebraically in the work here, all right, that's what I'm looking for, not just that the limit of this is equal to 3, okay, but how are you showing and how are you proving that this limit is in fact equal to 3, and it's done by this substitution. Now, let's try the next one. If we just, it always starts by checking to see if we even have an indeterminate form, right? Plug 0 in, we have continuity in the numerator and denominator, so plug in 0 and see what we get. But now we get, we get 0 in the numerator, sine of 0 is 0, but the denominator will also be 0, so we have a true indeterminate form. So that's where we say, well, what can we do then? We know we have 0 over 0, so let's try to get a combination that we know how to work with, a 0 over 0 combination. The numerator is not polynomial, so we're not going to deal with factoring up there. But we do have polynomial in the denominator, and we can factor out the removable discontinuity in the denominator, right? We can take out the x. And now we can split these apart into sine 3x over x times 1 over 5x squared minus 4. As long as we can run each of these limits and get a finite value, then the product of those values would be the value of the limit. Okay. All right, and yeah, that 1 I think is just a typo. It doesn't need to be there, that extra 1 floating around out there. Okay, so now we have the sine of 3x over x. I didn't include the work down here because we already did it up here. You would show that you do the substitution that we talked about up here to do this limit, this one right here. Let's choose theta is equal to 3x, x is equal to theta over 3. Therefore, this changes to theta going to 0, at least for this limit it does. And that gives us that this limit right here is equal to 3 for this first term. This term over here, right? You just plug 0 in and you see, because it's not a discontinuity anymore, and you get negative 1/4. So we end up with 3 times negative 1/4, you get negative 3/4. Okay, so this limit is negative 3/4. It starts by looking for an indeterminate form if we have one. Down here, x doesn't always have to go to 0, neither does theta. X is going to pi over 4 in this case. The tangent of pi over 4 is equal to 1. So we plug that in, we get 1 minus 1, 0 is the numerator. Check the denominator. The sine of pi over 4, that's root 2 over 2. And the cosine of pi over 4 is also root 2 over 2, so the denominator is going to 0 as well. We do get 0 over 0. So what do? It's a different exercise here. It's not the same as the other one. We weren't able to factor out a sine of x, for instance. We weren't able to get a sine of x over x kind of combination here. So we have to play around with the identities maybe a little bit and just try to find something that's going to work. And in this case, identities. If we turn everything into sines and cosines, maybe we'll see something that we couldn't see earlier. So I multiply top and bottom by cosine. Why? Well, tangent is sine over cosine. So we have a fraction inside of a fraction. We can eliminate that sine over cosine, that fraction, by multiplying through by cosine. Okay? So I'll multiply top and bottom by cosine. Then the numerator would become cosine x minus sine x. And the denominator, notice, we don't want to distribute the cosine because we already had a sine x minus cosine x. And that's great because now these two factors cancel, leaving behind a negative 1 because these two factors are opposites of each other. And now we can evaluate the limit now that we've removed a discontinuity. We have, in fact, right? Because if we rerun the limit, cosine x minus sine x again is equal to 0. So we have 0 over 0, but we get to cancel them with each other, leaving behind a negative 1. So we've removed the discontinuity. And we didn't have to use one of these kinds of limits, a sine of theta over theta, for instance, in this case. Remove the discontinuity, and then we can rerun the limit, we get this, negative root 2. So you have some similar limits to do in your homework as well. You have some also on the worksheet. Okay, here they are for you to try. Okay, you let me know if you have any questions on those. Okay, use proper notation. Right, I mentioned about writing the argument for the trigonometric functions. Use proper notation in order to, for instance, evaluate this limit, okay? You don't just, say 6 divided by 2 is equal to 3. That's not a way to prove what this limit is, right? Choose a substitution, use trigonometric identities, okay? Use some ingenuity, and see what you can do. All right? All right, I'm sure you can do this one. Let me know if you have any questions on it. You're given a position function. Find the velocity function, find the acceleration function, and then evaluate them. You're going to need to be able to evaluate trigonometric functions at different values of the input. You're in radian mode if you're doing this, okay? Whether we're in your calculator or whether doing this by hand, the input is taken to be a radian unless told otherwise. Okay? In fact, this t is actually representing seconds. But when we plug in t is equal to 2 pi over 3, we can interpret that input as a radian measure. Okay, it's flexible to that. If we meant degrees, we would have to see the degree symbol there. Let's find some more derivatives. Let's go for 2 derivatives. Find y prime and y double prime, given y is equal to x squared sine x. Okay, so y prime by use of the product rule. Let's see, we'll leave x squared alone and then multiply by the derivative of the sine of x plus, right, now we can take the derivative of x squared and multiply by the sine of x. All right, so I get x squared times cosine x plus 2x sine x. Okay, so I could leave the answer like that. Or we could simplify it. We could, factor out an x, leaving behind what? X cosine x plus 2 sine x, which is another simplification we could have. Okay. This step right here shows how we've applied the product rule. Okay, without any simplification or anything, just shows how we've applied the product rule. Now, what about the second derivative, right? Whether we took the result circled in green here or the other simplification, either way, we're going to be using product rules. And in fact, it looks like we're going to use 2 instances of product rules. Like up here, it looks like we're going to do a product rule for this product, right? And then a product rule for this product. So we would need 2 instances of the product rule. If we use this row down here, we're going to use a product rule to get this product right here. And then within this group, we have a second product. So we're still going to have to use the product rule twice. In using this one right here, we would have to use a product rule within a product rule. Okay, up here, we use 2 separate product rules, right? So it's up to you. Either way, you're going to get ultimately the same result. They should both simplify to exactly the same thing. All right, I'll take this one up here. Okay, so product rule on x squared cosine x. That would be x squared, okay, times the derivative of cosine x plus the derivative of x squared times cosine x. And then for the next term, we use another product rule. We have, 2x times derivative of sine x plus, right, could you say derivative of 2x or 2 times the derivative of x, right? Derivative of 2x times sine x, right? Just so you can see with all my notation here, this is how I'm thinking it through. So this is x squared times the derivative of cosine x is negative sine x plus the derivative of x squared is 2x. And then we're left with a cosine x plus 2x. Derivative of sine x is again cosine x. And then derivative of 2x is just 2 sine x. Always checking that this is with respect to the variable x, right? If this was like the derivative of 2x with respect to t, that would actually be equal to 0, right? The variable here in the Leibniz notation needs to match the variable in the function that you're differentiating, okay, in order to apply the normal rules of differentiation. Otherwise, if these variables don't match, you're just taking the derivative of a constant, right? So the Leibniz notation helps, in keeping clear which variable is the variable we're actually looking for. All right, so there's our answer by the use of a product rule then. Okay, it's a product rule right there. Let's see if we can clean this up. We have a negative x squared sine x. We have plus 2x cosine x plus 2x cosine x. Those combine to be plus 4x cosine x. And then we have a plus 2 sine x as well. All right, that's one way we could write it. Another way, I guess, let's see, 4x cosine x. All right, and then let's say I have plus sine x times 2 minus x squared. All right, that could be another way that we write it. Okay. Now, I'm not looking for the simplification that you get when you're only being asked to differentiate. If the instructions are just find the derivatives, then I'm looking for what I've circled in green. That you're showing me in your work, essentially, how you've taken the derivatives. Okay. All right. Same instructions. Find y prime and y double prime for how about y is equal to a quotient, sine of x over x. Okay, we'll find two derivatives. So, quotient rule, okay, low d high minus high d low over low low. So, low is x, okay, derivative of the high, I always feel like I should write it, low d high minus high d low, okay, low squared, right, or low low. So we have x is the low, the derivative of the numerator would be cosine x, minus the numerator is sine x, the derivative of the denominator is 1, and the denominator squared would be x squared. So that shows that we've used the quotient rule and that we got all the correct terms written out and factors within those terms as well. Okay, so that shows all the work right there. But if I want to move ahead to take a second derivative, I might want to clean this up maybe just a little bit. So there you go. X cosine x minus sine x over x squared. Okay, and you go even further than that. I can split this up. This is x cosine x over x squared minus sine x over x squared, which is the same as cosine x over x minus sine x over x squared. Right? We could use any one of these forms. So let's pick one of those for our second derivative then. Okay, I'll take this one right here. Okay, it is another quotient, so a second instance of a quotient rule. And within that quotient rule, it looks like we're going to be dealing with another product rule as well. Okay, quotient rule, low d high. So we start with x squared is low, and then we need the derivative of the numerator. All right, I'll write that we're taking the derivative of the entire numerator. The derivative with respect to x of x cosine x minus sine x. Okay, so low d high minus high, which is the quantity x cosine x minus sine x, d low. Okay, so derivative with respect to x of x squared over x squared squared. Okay, so let's see, we have x squared times, now let's take the derivative here, we need a product rule. Okay, we're going to need a product rule to deal with this x cosine x. Let's do that. So we have x times the derivative of cosine, that's a negative sine x, plus the derivative of x, which is 1, times the cosine of x. All right, that's our product rule right there. So now we have the derivative of minus sine x, so that's minus the derivative of sine x. Derivative of sine x is cosine x. And then minus the quantity x cosine x minus sine x times the derivative of x squared. Well, that would be 2x. And then this is over x to the 4th. Okay, let's see if we can clean this up a bit. So we have x squared times negative x sine x. And we have these cosines will cancel each other out right here. And then, let's see, minus 2x times x cosine x minus sine x. And this is over x to the 4th. So we have an x in each of these groups and an x down here. We can cancel those. So I'm going to be left with negative x squared sine x after canceling an x. Right? And then minus 2x cosine x, and then plus 2 sine x over x cubed. Right, so that is I've canceled one of these, I've canceled this, and I've canceled this. Okay, I turn it into a 3. All right, so that would be a simplification we would have then for the second derivative of the original function. Let's try one application. Let's see. Maybe 2. How about this one? Let's evaluate. Find f double prime of pi over 4 if f of x equals the secant of x. Okay, so we'll start by finding f prime of x, and then we'll find f double prime of x. You can plug in pi over 4. So f prime of x is the derivative of the secant of x. Okay, if you've already proven at this point what the derivative of the secant of x is, right? According to the worksheet, okay, we're using this right here. Right? Recall the derivative of the secant x is secant x tangent x. Okay. Showed you earlier how you can prove that that derivative is true. So f prime of x then would equal secant x tangent x. Okay, it's first derivative. Now we need second derivative. So f double prime of x is the derivative with respect to x of secant x tangent x. For this, we can use the product rule and the fact that we know now the derivative of secant, which is secant tangent, and we have the derivative of the tangent as well. Right? Okay, so to recall, the derivative of secant x, right, is secant x tangent x. And the derivative of tangent x is secant squared of x. And we're going to use the product rule here. So we have the first term is secant x, and multiply that times the derivative of the tangent x, plus we have the derivative of secant x, which we're going to multiply by the tangent of x. So we have secant x times secant squared of x plus secant x tangent x times tangent x. Okay, let's simplify that a bit. We get secant cubed of x plus secant x tangent squared of x. Right, that's our f double prime of x, second derivative of secant. Now we can evaluate at the input pi over 4. So that is, we want to know what is the secant of pi over 4, and then cube that quantity, plus the secant of pi over 4 times the tangent of pi over 4 squared. Now, the secant of pi over 4, that is 1 over the cosine of pi over 4. Cosine of pi over 4 is root 2 over 2, so secant of pi over 4 is 2 over root 2, which in other words is the square root of 2. And the tangent of pi over 4, which is the sine of pi over 4 over the cosine of pi over 4, tangent of pi over 4 is equal to 1. Okay, so f double prime of pi over 4 is equal to square root of 2 cubed plus the square root of 2 times 1 squared. That is 2 root 2 plus root 2, which gives us 3 square root of 2. Alright. So f double prime of pi over 4 is 3 square root of 2. Okay. One more exercise. Find all points, let's see, on the graph of f of x equals x plus sine x, all the points on that graph where the tangent line is horizontal. Okay, tangent line is horizontal. In order for the tangent line to horizontal, that means the slope of the tangent line, which is f prime of a, would have to equal 0. All right, so the slope of the tangent line is 0. So we need to find the derivative. Let's start by finding f prime of x. F prime of x is going to be 1 plus the cosine of x. All right. So establishing that, we're being asked to find information about a derivative here. Okay, so we need to find the derivative of our function. That's the first thing. Then we need to set our derivative equal to 0 because that's where we would have horizontal tangent lines. So we're going to solve the equation now. 0 equals 1 plus cosine x. And we're going to solve for all values of x that make this equation true. So this is the same as saying that cosine x is equal to negative 1. Cosine x is equal to negative 1. Okay. Where's the cosine x equal to negative 1? Right. For instance, we can look at a graph of a cosine function. Right. Y equals cosine x. Right. It's equal to negative 1 at many points, an infinite amount of points. So cosine is equal to negative 1 at values like pi. And then this would be 2 pi, and then this would be 3 pi. Right? This would be at negative pi and at negative 3 pi. So all odd integer multiples of pi. Right? Odd integer multiples of pi. Okay? So how do we write odd integer multiples of pi? Well, we can choose k to be any integer. We can write k is an element of the set of integers this way. Okay? Capital Z with a thick bar right here, a double bar. That's the set of integers. If k is any is an element of the set of integers z, right? Z is 0, plus minus 1, plus minus 2, on and on and on. That is the set of integers. Okay? We can use then for any integer the combination 2k plus 1 or 2k minus 1, either one, well 2k plus 1. Notice that if we choose now any integer and we double it, that would give us an even number. 2 times k is always going to be even. But then if we add 1 to an even number, we would always get an odd. So we can take x is equal to 2k plus 1 times pi. That would be a way symbolically that we can state that we're taking all of the odd integer multiples of pi. So like for instance, if k is equal to 0, then we're saying that x is equal to 1 pi. K is equal to pi. This one right here. If k is equal to 1, the next integer up, if k is equal to 1, then we're saying that x is equal to 2 plus 1 times pi, in other words, 3 pi, which is the next one. This one right here. If k was equal to -1, we would be saying x is equal to -2 plus 1 times pi, which in other words is negative pi. That would be this one right here. And if k is equal to -2, then we're saying that x is equal to -4 plus 1 times pi, which is -3 pi, which would be this one right here. And so on, right? Etc. Okay, so this is a way that we can say that we're finding the x values, okay, such that the cosine of those x values will equal -1. And if the cosine of that x value is equal to -1, then that means that the derivative is going to equal 0. Right? So in other words, we're saying f prime of 2k plus 1 pi will always equal to 0, okay, for all integers k. All right? So the derivative is equal to 0 if we plug in any odd integer multiple of pi. Now, we're asked to find the points on the graph. Points on the graph. Those would be points that would be coordinates x, y. Well, we now have the x coordinates of those points on the graph, not on the graph of cosine, on the graph of this, x plus sine x. You want to take a look at the graph of x plus sine x. Take a look at that. It's like a sine curve that sort of rises up towards the right along the trajectory of y equals x. So it's a combination of y equals x and y equals sine x by addition. X plus the sine of x. Let's see. There we go. Okay. See if it doesn't look too much like a line if we do it like this. Okay, so it's like a sine wave. It actually is like a sine wave. It actually is undulating, but it moves along the trajectory like y equals x. Okay, now in order to find the y values for these points, we can plug our x values into the original function. That is, let's evaluate f of x, okay, at these odd integer multiples of pi. So what is f of... Okay, that's for y values now, right? The y values. F of odd integer multiples of pi. Okay. That would be, now the function was x plus the sine of x. So that's going to be 2k plus 1 times pi plus the sine of 2k plus 1 times pi. Okay. Now the sine of any integer multiple of pi is always equal to 0, right? So this right here, that's equal to 0, right? Because the sine of any integer multiple of pi is always equal to 0. So we're just left with this quantity right here, the same quantity. So that means that y is also equal to 2k plus 1 times pi. So the points are the points xy with coordinates, where both the x and the y coordinates are equal to this 2k plus 1 times pi. Okay. So we got to use trigonometric derivatives here, along with the general power rule for x, right? We didn't have to use the limit definition to do this one, right? We had to use our geometric sense to understand that what this is telling us to do is that we need to set our derivative equal to 0. Not plug 0 into our derivative, but find the values we would need to plug in to get 0. And that left us with solving a trigonometric equation. Trigonometric equations, in general, will have an infinite amount of solutions. Okay, we're dealing with a domain of all real numbers here for this particular case. We had infinite solutions to get. Okay, so we had to find those infinitely many solutions in a compact form. We weren't able to list them all, out to infinity, but was able to write them in a more compact form. And then we had to find not just those x values, the inputs, we actually wanted the points on the graph, so we needed the y values as well. So we needed to plug those x values back into the original function in order to determine the y values. Okay, so that's a lot of work with the trigonometric functions here. All right, so that is it for this section. Okay, check out the homework and let me know if you have any questions, and work on the worksheet as well. Take a look through the notes at the exercises I worked through for you, and try out those worksheet exercises as well. Let me know if you have any questions on this content. Okay, take care.